Welcome to Night Lesson. Relax and learn along the way. Imagine you are standing at the edge of a deep chasm. Before you lies a world you know and understand, yet it is beginning to gently crumble at its edges. Behind you, unseen and unexplored, a completely new land awaits. It was precisely at this threshold that a man once stood, whose only wish was to save the old, familiar world. But out of his desperation, he unintentionally created something so radical that it would change the entire landscape of science forever. Max Planck, a name that often stands in the quiet shadow of Einstein or Heisenberg, was the unwilling midwife of modern physics. He himself called his revolutionary idea an act of desperation, a mathematical crutch in which he initially did not truly believe. A small, almost arbitrary-seeming assumption he made only to solve a stubborn problem. We delve into a time of upheaval, the turn of the 20th century. Classical physics, a magnificent edifice of logic and certainty, was reaching its limits. Like the gentle evening light falling on the old walls of a venerable university, a single, unsolvable riddle illuminated the cracks in the foundation of knowledge. Join us on a journey through the life of a man whose scientific discoveries turned the world on its head, and whose personal life was marked by deep, silent tragedies. It is a story of unintentional revolution, of human perseverance, and of the quiet, almost meditative beauty of scientific thought. Let us immerse ourselves together in the fascinating world of Max Planck and the beginnings of quantum physics, as the world around us slowly and peacefully settles into stillness. Chapter 1. The World Before Quantum Light. The late 19th century was a time marked by a deep, contented sigh of relief in the world of physics. The universe seemed to be a grand, elegant clockwork, its secrets almost completely deciphered. In the celestial vaults, the planets danced according to the immutable laws of Isaac Newton, their orbits as precisely predictable as the fall of an apple from a tree. And through the world flowed the invisible currents of electricity and magnetism, captured and unified in the beautiful equations of James Clerk Maxwell, which even explained the very nature of light itself. It was a magnificent edifice of knowledge, whose foundations seemed unshakable. It was believed that future generations of physicists would only need to fill in the last, tiny gaps and measure the known values with ever greater accuracy. In this world of supposed completion, a young man named Max Planck grew up, born in 1858 in the port city of Kiel. His family home was a sanctuary of education and culture, his father a law professor, the family imbued with a deep respect for knowledge, duty, and order. The young Max was a thoughtful child, whose interests spread in many directions like the branches of a tree. Yet when he chose to study physics, his esteemed professor in Munich, Philipp von Jolly, advised him against it with the best intentions. In physics, he said, essentially everything of importance had already been discovered. It was a completed science. What the professor could not see was the particular depth in Planck's character, a depth that revealed itself not only in science, but also in music. Planck was an exceptionally gifted pianist, and for a time even considered a career as a concert pianist. For him, music was far more than a pastime. It was a way of understanding the world. When his fingers glided over the keys of a grand piano, and the complex harmonies of Bach or Brahms filled the room, this was not a contradiction to the cool logic of physics. On the contrary, in the mathematical structure of a fugue, where themes and counter-themes weave together into a perfect whole, he sensed the same universal order he also sought in nature. For him, music was the emotional sister of mathematics, a language that could express the hidden harmony of the cosmos long before a formula could. Despite his professor's warnings, Planck dedicated himself to physics with quiet perseverance. He chose a field that many considered exhausted, thermodynamics, the study of heat. He was fascinated not by its practical application in steam engines, but by the philosophical power of its laws. The second law of thermodynamics, the law of entropy, particularly captivated him. It was this principle that explained why heat always flows from a hot body to a cold one and never the other way around, why a shattered glass never reassembles itself. Entropy gave time an irreversible direction and seemed to be an absolutely valid, universal law. This search for the absolute reflected Planck's deep inner nature. He was a man who believed in a divine, rational order in the universe. For him, science was a way to trace this order, to comprehend the thoughts of the Creator. Classical physics, with its predictable and harmonious world, seemed to perfectly fulfill this longing. The universe was understandable, orderly, and beautiful. No one yet suspected that he, this thoughtful, order-loving man, would be the one to set in motion the events that would cause this perfect edifice to crumble. Chapter 2. A riddle called Black Body. The crack in this perfect edifice of physics was at first barely visible. It did not reveal itself in the distant movements of the planets or the great laws of mechanics, but in a seemingly simple, everyday phenomenon, the glow of a heated object. The physicists of that time had created a theoretical ideal for this, a concept of pure, undisturbed elegance. They called it the black body. One can imagine it as a cavity, perhaps a metal sphere, completely blackened on the inside, with only a tiny opening to the outside. Any light that enters through this opening is trapped inside, absorbed and reflected by the walls until all its energy has been taken up by the body. It is the perfect absorber of light. Now, if you heat this body, it begins to glow. A radiation emerges from the small opening, pure and uninfluenced by the outside world, a direct message of its internal temperature. And this is precisely where the riddle began. The experiments showed a clear and repeatable pattern. At lower temperatures, the light seeping from the cavity was a deep, warm red, like the embers in a slowly dying hearth. As the temperature was increased, the glow became brighter, changing to orange, then to a brilliant yellow-white. At extremely high temperatures, the color shifted further into the bluish range. The glow became more intense, more energetic. But when the theorists tried to describe this behavior with their proven laws, they hit an insurmountable wall. Their elegant formulas, which so reliably explained the rest of the universe, failed here in a strange way. One theory, which became known as the Rayleigh-Jeans law, worked wonderfully for the long, gentle waves of red and infrared light. It perfectly described how the energy was distributed there. But when the formula was applied to the shorter wavelengths, the blue, violet, and ultraviolet light, it predicted something utterly absurd. It claimed that the energy would have to increase to infinity. A heated oven, therefore, should have emitted an unimaginable amount of ultraviolet radiation, enough to incinerate everything in its vicinity. This obvious impossibility was given a dramatic name, the ultraviolet catastrophe. Another theory, Wien's radiation law, seemed to offer the solution, but it was only the other half of a broken mirror. It described the behavior at short, high-energy wavelengths very well, but failed miserably for the long, red waves. Physicists were faced with a graph on which lay the measured, gently sloped curve of reality. From the left, one theory approached and nestled against it, only to then drift off into absurdity. From the right came the other, fitting perfectly for a moment, only to also lose contact with reality. Max Planck did not see this problem as a catastrophe, but as a profound inconsistency, a dissonance in the otherwise harmonious music of physics. He was deeply convinced that nature does not make leaps and does not produce infinite absurdities. There had to be a single, comprehensive formula, a bridge that could connect these two incomplete halves and explain the gentle curve of observation in its entirety. In the silence of his study, driven by the desire to restore order, he immersed himself in this one, stubborn riddle that questioned the perfection of his world. Chapter 3. An Act of Desperation in the Silence. How many nights had he spent like this? In the deep silence of his Berlin study, with only the soft rustle of paper and the steady ticking of a grandfather clock for company. Max Planck, a man whose thinking was as orderly as the books on his shelves, sat over formulas that resisted him. Years had passed in which he tried to master the riddle of black body radiation with the proven tools of classical physics. He bent the laws of thermodynamics, stretched the assumptions of electrodynamics, but each time he ended up at a dead end. The equations he derived fit either at the high frequencies or at the low ones, but they never formed the single, elegant curve that the experiments so clearly showed. It was like trying to open the same lock with two different keys. The autumn of 1900 settled over the city. The leaves were falling, and a cool clarity was in the air. In Planck's mind, however, there was no clarity, but a growing exhaustion. All his attempts to stay on the orderly, continuous path of classical physics had failed. In a moment that was marked less by sudden enlightenment than by the deepest frustration, he decided to do something unthinkable. He would take a path he deeply abhorred, a pure formalism, a mathematical artifice that he hoped he could later eliminate from his equation. Imagine that energy does not flow like water in a steady stream, but falls like sand, grain by grain. Planck asked himself, what if the oscillators in the walls of the cavity could not release their energy in any arbitrary amount? What if they were forced to emit it in tiny but specific portions? He called these portions quanta. It was a hypothesis that contradicted everything he had learned and believed in. Nature, he was firmly convinced, does not make leaps. But the mathematics that resulted from this strange assumption was astonishing. To cast this idea into a formula, he needed a new number, a bridge between the energy of a packet and its frequency. He picked up his pen and wrote a letter on the paper that would change physics forever, a small h. This new constant, later called Planck's quantum of action, was the proportionality factor. The energy of a quantum, E, was therefore equal to its frequency, nu, multiplied by this tiny but fundamental constant, E equals h nu. Energy could thus only be emitted or absorbed in multiples of this smallest amount, no longer a gentle slope, but an infinitely fine staircase. When he completed the calculation, the resulting formula was a perfect fit. It clung to the experimental data like none before. But Planck felt no triumph. He regarded his creation with deep suspicion. He had solved the riddle, but the price was the introduction of an idea that seemed absurd to him. This, he told himself, was not a description of reality. It was an act of desperation, a purely mathematical trick whose deeper physical meaning he had yet to find, a meaning that would hopefully lead him back to the safe ground of the classical world. He did not suspect that, in the silence of his room, he had not only found a formula but had unintentionally pushed open the door to an entirely new universe. Chapter 4. The Quantum of Action and the Dawn of an Era. The 14th of December, 1900, was a cool, gray day in Berlin. In the venerable halls of the German Physical Society, an atmosphere of concentrated silence prevailed. Here, before his colleagues, stood Max Planck to present the fruits of his nightly labor. It was not a triumphant performance, not a dramatic revelation. It was the quiet, almost sober presentation of a man who had solved a stubborn problem. He presented his new formula for the radiation of a black body, an elegant equation that fit the lock of the experimental data like a custom-made key. It worked perfectly. Those present nodded in appreciation. The formula was accepted, just as an engineer accepts a new, better blueprint. It solved the ultraviolet catastrophe and brought theory and measurement into harmony. That was what mattered. But the deeper, unsettling implication hidden within this formula was scarcely noticed. It was heard, but not truly understood, not even by its creator himself. Because to derive the formula, Planck had to make a radical assumption. Energy is not emitted in a continuous stream, but in discrete, tiny packets, in quanta. With this assumption, a new fundamental constant had entered the world of physics, a small letter with enormous significance. H, Planck's quantum of action. Its value was unimaginably small, approximately 6.626 times 10 to the power of minus 34 joule seconds. A number with 33 zeros after the decimal point before the first digit appears. A quantity so minuscule that it seemed to play no role in everyday life. Yet this tiny constant was the foundation of a new reality. It was the grain from which the world is built at its smallest scale, the minimum unit of action in the universe. It dictated that nature, at its most fundamental level, does not proceed smoothly, but in tiny, indivisible jumps. While the world of physics gratefully accepted the practical formula, Planck struggled with the spirit he had called. In the years that followed that December lecture, he devoted a large part of his energy to a strange goal, to disprove his own hypothesis. He could not accept that nature should be so jerky, so inelegant. The quanta were, for him, a mathematical artifice, a temporary expedient that he had to replace with a deeper, classical explanation. He searched for ways to derive his formula without presupposing the existence of these energy packets. He was a reluctant revolutionary, a man who had pushed open the gate to a new era and was now trying with all his might to close it again. But the door could no longer be locked. The quantum of action, H, was now in the world a quiet, persistent question that echoed in the formulas and theories of physics. It was now up to a new generation of thinkers to see Planck's Act of Desperation not as an end, but as the true beginning. Chapter 5. The Seed Sprouts, Einstein's Light Quanta. Where did the beginning of this new understanding lie? Perhaps in a quiet office in Bern. Just 5 years after Max Planck had hesitantly presented his formula, a young patent clerk sat there at his desk. His name was Albert Einstein. The sunlight falling through the high window painted a warm patch on the wooden tabletop and the paper spread out there. But in this man's thoughts, light was more than just a brightness that illuminated the day. It was a riddle. There was a phenomenon known as the photoelectric effect, a seemingly simple process. When light strikes a metal surface, it can knock tiny electrons out of the metal, like a jet of water washing sand grains from a path. But classical physics struggled with the details. A very bright, intense red light, for example, could shine on the metal for hours, and nothing would happen. A faint, barely visible violet light, on the other hand, immediately dislodged electrons. It was not the strength of the light that mattered, but its color, its frequency. How could this be? Einstein thought about Planck's work, about the small packets of energy, the quanta, that Planck had introduced as a kind of mathematical trick to describe the radiation of a black body. What? Einstein wondered, if this was not a trick? What if it was the truth? What if light itself was not a continuous wave lapping at the shore of the metal, but a stream of countless, tiny energy packets? In his imagination, the beam of light became a hailstorm of discrete particles, which he called light quanta. Each of these particles, later named a photon, carried a precise amount of energy that depended directly on its frequency, just as in Planck's formula. E equals h times nu. Red light consisted of low-energy quanta, which did not have enough power to free an electron from the metal, no matter how many of them arrived. Violet light, on the other hand, consisted of high-energy quanta. Even a single one of these particles had enough force to send an electron on its journey. The intensity of the light only determined how many quanta arrived per second, not the energy of the individual packet. It was a bold, breathtaking idea, and when Einstein published it in one of 4 revolutionary papers in that miracle year, it was met with deep suspicion. Even Max Planck, the father of the quantum, shook his head. For him, his discovery had been a necessity, a strange property of matter, of the oscillators that emit light. But that light itself, which had been understood as a perfect wave for almost a century, should consist of particles, seemed absurd to him. He considered it youthful exuberance, a speculation that went too far. But the seed had been sown. Einstein's explanation of the photoelectric effect was too elegant, too precise to be ignored. Over the years, experiments confirmed his prediction. Slowly, almost reluctantly, the world of physics began to accept that Planck's discovery was far more than a mathematical curiosity. It was a window into a new reality. When Einstein received the Nobel Prize in 1921, not for his more famous theory of relativity, but for this work, the existence of light quanta was sealed. Light was now both a wave and a particle. And this strange dualism was only the first hint of how profound the changes would be that Planck's little h brought to our understanding of the universe. Chapter 6: A New World Order, the Quantum Revolution. What held the world together at its core? This question, as old as thought itself, now found an unexpected and wondrous answer. The idea of quantized energy, Planck's hesitant proposal, was like a key that fit a long-locked gate. The young Danish physicist Niels Bohr was one of the first to turn this key with a firm grip. He looked at the prevailing model of the atom, a small, dense nucleus orbited by electrons, and recognized its deep contradiction. According to classical physics, these electrons should have constantly radiated energy and inevitably spiraled into the nucleus. No atom should be stable. But Bohr took Planck's quantum idea and painted a new picture. Let us imagine this picture: a nucleus at the center, and around it, not just any orbits, but very specific, allowed ones. Like fine, luminous rings in the dark, on which the electrons circle without losing energy. An electron cannot simply move a little closer to the nucleus. It must jump, a quantum leap from one allowed orbit to the next. When it falls to an inner orbit, it emits a precisely defined pulse of energy, a single light quantum whose color corresponds exactly to the energy difference between the orbits. And to reach an outer orbit, it must absorb exactly the right amount of energy. The atom was no longer a mini-planetary system doomed to collapse. It was a stable, orderly structure whose laws were dictated by Planck's constant. This realization opened the floodgates. A new generation of physicists, young and fearless, plunged into this strange new world. Names like Werner Heisenberg, Erwin Schrödinger, and Paul Dirac appeared on the stage. They were no longer lone warriors, but part of a great intellectual conversation that spanned all of Europe through letters and conferences. Heisenberg formulated his famous uncertainty principle, which states that we can never simultaneously know the exact position and the exact momentum of a particle. The more precisely we measure one, the blurrier the other becomes. Schrödinger described the electron no longer as a tiny sphere, but as a wave function, a cloud of probability that spreads out in space. Solid, tangible matter dissolved into a play of potentials and possibilities. And Max Planck? He observed this stormy development from a distance, like a wise elder statesman. He saw how his discovery, which he himself had called an act of desperation, became the foundation of a theory that shook the very pillars of his own worldview. In his heart, Planck remained a follower of classical physics, of the deterministic universe where everything follows a clear cause and effect, like a precise clockwork. But now the young physicist spoke of chance, of probability as a fundamental principle of nature. He was proud of the fruits that had grown from his seed, but the world they described was alien to him. He had to watch as the order he had wanted to save was replaced by a new, much deeper and stranger order. Certainty gave way to probability. The clear path of a particle became a shimmering cloud of possibilities. The revolution he had unintentionally started was now unstoppable, and its echo would forever change the way we view reality itself. Chapter 7: The Parliament of Physics, the Solvay Conferences. It was a cool November day in the year 1911. In the elegant halls of Brussels' Hotel Metropole, where light fell through high windows and caught in the polish of old mahogany tables, 24 men and 1 woman gathered. Not just any people. The brightest minds in physics from around the world, convened by a Belgian industrialist named Ernest Solvay, who wanted to dedicate his wealth to a single question: what did Planck's quanta really mean? Max Planck was there. He sat among Einstein, Curie, Lorentz, Rutherford, Poincaré, among men and a woman who had rewritten the universe. And yet, he was something special at this table. He was the originator. His name was not just on the invitation list. It was at the center of the question itself. The quanta, which he had born out of necessity 11 years earlier, were now the central theme of this first Solvay conference. A mathematical crutch had become the subject of international scholarly debate. One can imagine what he felt in those days. Pride, perhaps, but also a deep uncertainty that he could not entirely hide. For while the younger attendees discussed the quantum hypothesis with growing enthusiasm, the old doubt remained alive in Planck. He had not birthed this idea out of conviction, but out of desperation. And now, all of physics looked to him as the father of a revolution in which he himself still did not fully believe. 16 years later, in October of 1927, the great physicists found themselves in Brussels again. The fifth Solvay conference was to become the most famous of all. A photographer captured a moment for eternity. 29 physicists, including 17 future or current Nobel laureates, gathered like the founding fathers of a new world. Planck sat in the front row. He was now almost 70 years old, his hair gray, his face etched by decades of thought and life. At this conference, perhaps the most significant scientific debate of the 20th century erupted. Albert Einstein, still relentless in his faith in causality, resisted the core tenet of quantum mechanics, the idea that the universe, at its deepest level, is not deterministic, but profoundly random. Einstein, who in those years repeatedly said that God does not play dice, spoke it with a conviction that echoed through time like thunder long after the lightning has passed. Niels Bohr replied calmly but unequivocally, Einstein should stop telling God what to do. Planck listened. In this debate, he stood between two men he loved and admired, and he recognized himself in both. In Einstein's longing for order, for a universe founded on eternal laws, and yet, in the quiet knowledge that the 14th of December, 1900, had left him, that nature does not always answer as one wishes. Sometimes, it dictates its own terms, and one can only choose whether to follow them or not. The Solvay conferences became the place where the minds of modern physics met, wrestled with one another, and moved on. For Planck, they were also a mirror, a glimpse of how far the light of a single act of desperation could shine, farther than he could ever have imagined. And into this luminous distance, in those Brussels autumn days, he also carried the shadows that had long since become a part of him. Chapter 8: The Price of Duty, Planck and the First World War. The summer of 1914 broke over Europe like a thunderstorm that had long been on the horizon. The shots of Sarajevo rolled as an echo through cabinet rooms and general staffs, until one nation after another was drawn into the vortex of a war whose full cruelty no one foresaw. Max Planck, the physicist of silent natural laws, the man who thought in formulas and constants, suddenly found himself in the midst of another storm. He signed. Like many of his colleagues, Planck was swept up in the wave of nationalism and put his name to the appeal to the cultured world, that declaration by 93 German intellectuals who defended Germany's conduct of the war and dismissed reports of atrocities as enemy lies. It was a decision he would deeply regret in the years that followed. A man of thought who, in that moment, had not thought through where such a war would lead. The conviction was still strong that one must serve the fatherland, with the mind, with the name, with the dignity of science. Science took a stand. Planck's good friend Fritz Haber, a chemist and patriot, turned his genius to the development of chlorine gas as a weapon of war, convinced that a swift end to the war would save more lives than a long one. In April of 1915, the first clouds of gas rolled over the trenches in Ypres. Planck watched in silence. There are no recorded words that describe his inner struggle in those days. Only the silence, which is hidden deep between the lines of letters and diaries. But while science was in the service of death, death also struck Planck personally. In the autumn of 1916, Karl, Planck's eldest son, fell at the front at Verdun. He was 28 years old. For his father, who had dedicated his life to the search for order and truth, this loss was like a crack in the fundamental structure of reality. No formula explains why a young man must die. No theory gives comfort when a letter from the War Ministry lies on the desk, and the light in the room suddenly seems colder than before. Planck kept writing. He researched, he taught, he remained, outwardly, the calm, dignified man of science. But those who knew him reported a deeper gravity that had etched itself into his face, a shadow that never again disappeared. When the war finally came to its bloody end in November of 1918, Germany was shattered, humiliated, and exhausted. In that very same year, Planck received the news from Stockholm. He was to be awarded the Nobel Prize in Physics. The discovery, that act of desperation from the year 1900, was now officially recognized as the foundation of a new era. The highest prize in science, in a year when the country lay like a wounded animal. Planck received the honor with dignity, and with a silence in which perhaps two irreconcilable truths met: the joy of recognition and the pain for the son who would never be able to share that joy. The world had changed. Germany had changed. And Planck himself, the man who once believed that reason and order would always find their way, now carried within him a premonition that could no longer be dispelled, that history sometimes takes paths that obey no law of nature. Chapter 9. The Nobel Prize and the Burden of Fame. 18 years is a long time, a span in which an idea can grow from a radical hypothesis into a foundation. It was not until 1918, as the echoes of a world conflict slowly faded, that Max Planck received the news from Stockholm. The Nobel Prize in Physics was to be awarded to him. A heavy, golden disc, lying on a cushion of dark velvet, the light caught in the engraving of Alfred Nobel's profile. It was more than just an award. It was the official recognition of a revolution he had never wanted. The citation was precise and clear, like a physical formula, in recognition of the services he rendered to the advancement of physics by his discovery of energy quanta. Energy quanta, those small, discrete packets of energy he had postulated in an act of desperation, were now part of the vocabulary of science. The recognition came late, but it came with force. It cemented his place not only in the history of physics, but also in the public perception. He was no longer just a brilliant theorist. He was a national icon, an elder statesman of science. His life shifted from the quiet studies and hushed lecture halls out into the bright light of the public sphere. He became a leading figure in the Kaiser Wilhelm Society, the forerunner of the later Max Planck Society, an organization founded to promote the country's best minds and give them the freedom to conduct their research. His place was now often in the large, wood-paneled halls, where light fell through high-arched windows and dust particles danced in the beams like tiny planets in a solar system. There he spoke, not with the fire of a revolutionary, but with the deliberate, considered voice of a man who felt the weight of tradition on his shoulders. A silent struggle continued to rage within him. He saw himself as a bridge builder between the old, familiar world of classical physics and the new, strange continent of quantum mechanics. He admired the boldness of the young generation around Bohr, Heisenberg, and Schrödinger, yet he could never fully follow their most radical conclusions. The idea that chance should be a fundamental component of nature was repugnant to his deep belief in causality and order. Thus, he became a moral authority who advocated for open, respectful debate, even as he no longer determined the direction in which the current flowed. With fame grew the burden of responsibility. His words carried weight, far beyond the borders of physics. He became one of the most important voices of German science at a time when the political clouds over the country were beginning to gather menacingly. The dignity of the Nobel Prize was not just a glow that fell upon him, but also a commitment to stand up for reason, integrity, and the freedom of research. This voice, now endowed with the weight of the highest prize in science, would soon be put to the test in a way he could never have imagined in his quietest hours. Chapter 10: Shadows over Germany. Planck in Turbulent Times. The glow of the Nobel Prize seemed to fade quickly in the gathering twilight. The commitment he had felt so deeply, the duty to stand up for reason and the freedom of research, was put to a test that made all previous scientific debates seem like distant, harmless thought experiments. A shadow began to fall over the country, a dark, cold shadow that crept into the lecture halls, the laboratories, and the hearts of the people. It was 1933. With the seizure of power by the National Socialists, a new, icy wind blew through the venerable halls of German science. A wind of intolerance and hatred. The so-called purge of the universities and research institutes began systematically. Colleagues with whom Planck had debated, researched, and taught for decades were suddenly declared enemies of the state, solely because of their Jewish heritage. Names like Albert Einstein, James Franck, Max Born, the architects of the new physics, were struck from the lists. Their chairs in the academies remained empty, their voices silenced. It was as if a finely tuned clockwork were being smashed with a hammer, like the shattered glass of a test tube lying on the cold stone floor of an abandoned laboratory, a symbol of the destruction of knowledge and humanity. As president of the Kaiser Wilhelm Society, the flagship of German research, Max Planck felt it was his duty. He was not a man of loud protest. His character was shaped by Prussian restraint and a deep belief in the order of the state. But he could not stand by idly. In an act born of a mixture of duty and desperate hope, he personally sought a meeting with Adolf Hitler. He tried to argue with the language of reason, explaining to the new Reich Chancellor that Germany was destroying itself by driving out its best scientific minds. But his words bounced off a wall of ideological delusion and ice-cold lust for power. Planck left the meeting a broken man, having recognized the full depth of the barbarism that had descended upon his country. This loss was tragically embodied in the fate of his friend Fritz Haber. Haber, a Nobel laureate in chemistry, a fervent German patriot who had pioneered the development of chemical weapons for his fatherland in the First World War, was of Jewish descent. His merits counted for nothing. He was forced to abandon his life's work, his institute in Berlin-Dahlem, and go into exile. A few months later, on the way to an uncertain future, he died in Switzerland, homeless and with a broken heart. Planck's memorial service for Haber, which he organized against the express will of the regime, was a quiet but unmistakable act of defiance. Planck was later criticized for his resistance not being loud enough, not revolutionary enough. He chose to stay, hoping to protect the structures of science from within and preserve them for the time after the tyranny. It was a lonely, painful path. He must have often stood at his office window, his face etched with worry, looking out at a world whose familiar order had come undone. His resistance was not that of a clenched fist, but that of a hand trying to shield a flickering candle in a storm. A candle of reason and human dignity in the darkest night of German history. Chapter 11: Personal Tragedies and an Unshakable Spirit. But the storm that engulfed the world did not only rage outside, in the alleyways of Berlin and on the battlefields of Europe. Another, quieter, And perhaps even more merciless storms swept through the personal life of Max Planck, leaving almost nothing standing. The great, universal laws to which he had dedicated his life seemed to offer no comfort in the face of the deep, personal wounds that fate dealt him. It was as if the universe revealed its orderly secrets to him while his private happiness disintegrated into chaos. The losses began early and never truly stopped. His first wife, Marie, the love of his youth, passed away after a long illness, leaving him with 4 young children. A faded photograph from happier times might have stood on his desk, a silent witness to a time when a family's laughter filled the rooms. But fate was not yet finished. The First World War took his eldest son, Karl, at the front at Verdun. A pain that etched itself deep into the father's face, a new, permanent line of sorrow. He lost his twin daughters, Greta and Emma, tragically and in quick succession, shortly after childbirth. 4 of his children had been taken from him, and only one son, Erwin, remained from his first marriage. This last remaining son became the center of his fatherly love and concern. Erwin was a man of principle, a high-ranking official who, like his father, believed in the dignity and reason of man. But in Germany's darkest hours, this belief was not enough. Erwin joined the resistance, was part of the circle involved in the 20th of July, 1944 plot, the attempt to end the tyranny. The attempt failed. Erwin was arrested, tortured, and sentenced to death. One can imagine the old, now elderly Max Planck, using all his remaining influence, all his scientific prestige, to save the life of his last son. He wrote letters of appeal to the highest authorities of the regime, but his words went unheard. In January 1945, Erwin was executed. This was the final, the most unbearable blow. The light of reason, which he had defended his entire life, now seemed to have been extinguished for good. His house in Berlin was destroyed by bombs, his irreplaceable library, the records of a lifetime's work, burned to ashes. He fled the destroyed city, a broken but not defeated man. Those who saw him in those days reported that he would sometimes sit down at a stranger's piano, wherever he found shelter, and play softly, Bach, Brahms, the old harmonies. Not as an escape, but as a reminder that there is an order greater than human suffering. It is an almost incomprehensible image. This thinker who had reordered the foundations of reality, now sitting amidst the ruins of his own life. And yet, even in this deepest darkness, there was something in him that did not break. His belief in a fundamental order, in a truth greater than human suffering, sustained him. Like a small, green shoot, fighting its way through the rubble of a bombed-out house in the moonlight, the conviction continued to grow within him that behind all chaos, a deeper lawfulness must lie hidden. This search for truth became his final anchor in an ocean of pain. Chapter 12. The Legacy of the Reluctant Revolutionary. After the Great Storm, little more remained of a once orderly world than a small, humble room in the old university town of Göttingen. No professorship, no private library, no grand piano under his fingers, just a narrow bed, a simple table, and a window with a view of unfamiliar roofs. A fall in the last years of the war had marked his body, and the hardships of the flight from bombed-out Berlin did the rest. Cared for by his second wife, Marga, Max Planck spent his final months in this modest refuge, stooped and weak, yet with a clarity of mind that had never left him. There were no more award ceremonies, no crowded lecture halls, no audiences with the powerful. Only the silence of a room where one of the most significant minds of his century now simply breathed, grateful for each new day. On the 4th of October, 1947, in this humble room, he closed his eyes forever. No pomp accompanied his death, no grand ceremony, just a quiet fading, almost unnoticed by a world still preoccupied with its own rubble. And yet, he left a legacy almost too vast to comprehend. A few months later, the resurrected Kaiser Wilhelm Society, of which he had once been president, would bear his name, the Max Planck Society, a monument of living research that he himself did not live to see, but whose foundation was his entire life's work. It is a silent legacy that pulsates in the world around us. Every laser beam that sends data through fiber optic cables, every glow of an LED screen, every transistor in the tiny microchips that power our modern world, they all bear the invisible signature of his quantum of action. From the development of quantum electrodynamics, which describes light and matter, to modern particle physics and quantum field theory, which trace the fundamental forces of the universe, they all build on the foundation he laid in a single, desperate night. And yet, he was never a revolutionary by conviction. He was, rather, a reluctant revolutionary, one who was led by the relentless logic of his own discovery to a place he had never wanted to enter. He was like an old captain who loved the familiar coastlines of his classical physics, yet was forced by the mere observation of the stars to draw a completely new, foreign world map. His life is a profound testament to the fact that the greatest leaps in knowledge do not always arise from bold will, but sometimes from intellectual necessity, even when they shatter one's own deepest convictions. Perhaps his greatest legacy, however, lies not in the formula alone, but in his attitude. Planck never saw science as a mere instrument for mastering nature. For him, it was a path to reverence, a bridge from physics to metaphysics. He believed in an objective reality outside our consciousness and saw the search for its laws as a deeply ethical task. Science, he believed, should not make man arrogant, but teach him humility before the infinite complexity of the cosmos. Thus, Max Planck remains an inspiration that extends far beyond his scientific genius. He stands for the unshakable perseverance of the human spirit, for dignity in the face of suffering, and for the courage to follow a truth even when it shatters one's own world. Like an old, gnarled tree, its roots anchored deep in the classical earth, yet its branches grow unstoppably into the new, vast sky of the quantum world. So stands his work, a symbol of the eternal dialogue between the known and the unknown, between order and the unimaginable mystery that lies at the heart of everything.
That was today's night lesson. Thank you for listening. If you'd like to see more videos like this, please leave a like and subscribe to the channel. Good night and sleep well.